Hello. Yeah, here we will look at squares modular a power of an odd prime. So let P be this prime. And examine when an integer is a square modular power of this prime. The clear necessary condition is that reduced down modulo to modulo p, that should still be true. So at least this implication is obvious. And that, of course, is solvable. So, solvable. Let's add this. So this is solvable if and only if now what we call the Legendre symbol is 1. But what we're going to show is that this goes both ways. So the only condition for that to be solvable, modular any power of a odd prime, is that it works modular the prime itself. Let's go with an argument, and it will be an inductive step, so we will be starting from this base and increasing powers one by one, reaching this power. And so we just need to present the step. Assuming that I already have a square root of a modular some power, I need to construct a square root of the same a modular the next power. So this I have, this I am building. What do I know about this new y? Well, reduced modular this previous power, it should coincide with either with any root. And at the same time as we prove this criterion for solvability, we'll really describe all the roots. And the roots are so two solutions. And the roots will be always different by -1. So they're just two solutions for any power. And yeah, it's sloppy, but it's really plus or minus fixed solution. So I assume that I already have it for the power m. I have two solutions for this congruence, and then I'm picking up one and I'm lifting it. That's a method of lifting to the to a solution, and it will be a unique one, modulo the higher power. So lifting a fixed x, I can then assume that y is congruent to this x when looked at modulo the previous power. So that is the condition that I'm lifting x. And yes, we can write it in integers or in congruences mode, this next power as x plus some multiple of that power, of the previous power. So that's what we know about such lifting. Just that is exactly to be lifting. And all what is left now is to plug it in and see what happens when we compute the square. And when we compute the square, we will have x squared, and then we'll have twice x p to the m u, and then we'll have the square of this. But the square of this is going to disappear because I'm looking at this square modular p to the m plus 1. So the square of this will disappear because it will be p to the 2m And 2m is going to be not smaller than m plus 1, so going to be 0. So hence this congruence. Now I'm going to use the fact that x squared, at least modulo p to the m, is a. So that rewritten will be saying that modulo p to the m plus 1, it is a plus some other multiple of p to the m. And then what I can substitute here, and I'll have a, that's what I want after all, and then an addition, and then another addition, so now I'll put p to the m in front, and then I'll have 2xu. So my freedom in the story is u. V is whatever it is, because x is whatever it is, whatever was already found, say, at the previous induction step. But u is my freedom, and I can choose it to be whatever I like. So what do I need to choose to make this all disappear? Right? I want to make this disappear because I want to have just a. That's my lifting condition. So the disappearance is equivalent to that being congruent to 0 modulo p to the m plus 1. So let me write it. Now factoring the previous power altogether out. If we look at what it says in integers, it will be saying that p to the m times this sum is a multiple of p to the m plus 1, say w. And in integers we can cancel p to the m safely, and then we will have v plus 2xu being equal to that w times p. 1 power of p will survive. And bringing it back to the congruences, we could just say that v plus 2xu is congruent to 0 mod p. And u is whatever I want to find to make it happen, and we can, because p is odd, x is something square into something non-zero, presumably, mod p, and that is guaranteeing that x is itself invertible mod p, so we can find the inverse to 2x, and hence we can find the solution to u. It will be with negative sign, because v will have to be put on the other side of the equation. The inverse of 2x times that v. So that is mod p. And that is all we need to know about u, actual u. It's remainder mod p, because we're going to use not just u, but u is a product with mth power of p, and modulo p to the m plus 1, it's only the remainder of u mod p we're interested in. And that is it. So that is the lifting. Y is to be found this way. So that will be p to the m, v, again v is given, because x is given, and then 2x all inverted, and again it's all given, because x is given, and that is all to be computed as a equivalence class, congruence class modulo p to the m plus 1. So that's a process which can be performed unstoppably, lifting any of the two roots of this equation from that congruence level to this congruence level. Hence the statement. Let's put it to practical use. The scheme is actually quite practical. So let's choose a prime, p, say, being 11. And you could check that modulo 11, 5 is a square. 5 is a square of 4. So the congruence x squared congruent to 5 mod 11 has a solution. So 5 is a quadratic residue mod 11. Actually two solutions, so the solution, say one of them will be 4. 4 squared is 16, and reduced down to its remainder mod 11 is 5. And negative 4, which is as good as 7, is also working. So 7 squared is 49, and without 44 is just 5. So these are the two solutions we have. X is congruent itself to plus or minus 4 modulo 11. So now let's solve the congruence at the next power of 11 squared, which is the same as 121. The same method, the very method we used, and we write the new x. So yeah, it's the same x. Maybe I should really well, it's okay, because reduced down to modulo 11 it will be just the same x. So let me choose which of the two solutions modulo 11 I will be lifting. I will choose plus 4, and then this equation becomes 11 times some number u. So this will be finding, and I'll be finding it just by computing this square of this and matching it with 5. So x squared, which is 4 plus 11u squared, has to be congruent to 5 mod 11 squared. What it is on the nose is 16 plus, I will write it as a product 8, which is 4 times 2 times 11u, and then there will be 11 squared, which is not interesting really, because I am reducing it all mod 11 squared. And now I have to match it with 5. So that's the condition really which going to give me my u. And I can put 16 on the other side of this congruence, and that will bring me closer to my u by giving me on the right negative 11. And now I can just cancel out 11s throughout the congruence, including the modulus. That's what I did here by bringing it to the equation of integers and then doing cancellation there. So that will be 8u congruent to negative 1 mod 11. That is where I will find my u finally. I need to invert 8. So maybe I will change negative 11 to positive 10 and then cancel out one copy of 2 because I can. 2 is invertible mod 11. So that will be bringing me down to 4, u being equal to 5 mod 11. Now I have to invert 4. Well, it's easy. 4 times 3 is 12, 1 plus 11, so the inverse of 4 is 3. So well, u is the product of 3 and 5, which is 15. And 15 reduced to its remainder mod 11 will give me 4 again. And that now is the key for finding my x. So x, the lifting of the positive root mod 11 to 11 squared, is given by this. It's 4 plus 4 copies of 11. That's what it is, modulo 11 squared. So that can be simplified to 4 times 12, which is just 48. And so I have one lifting of the positive 4 to 48 modulo 11 squared, and the negative 4 you could check lifts to negative 48. And that will continue forever. You will always have one lift for one root at the previous power of 11 when you will be upgrading to the next power. So that's it. See you later.